All right, so now we'll go on to the next topic. This is also going to. This next topic is again going to challenge the way that you look at numbers themselves. So this topic is converting between bases. Some people may have seen this before. My guess is most of you have not. So before I talk about what this is and what it means and how to do it, I want to give you a little background of something related to this that you may have heard of. Who has heard of binary data? Who knows what that is? Okay, what is it? Ones and zeros. Absolutely. This is so. I think everyone's heard of ones and zeros for the way the computers encode numbers and information. Okay. Well, when you see a computer write down the number 1011, what is that? It's a code. What does it mean? Okay. Well, that's what we're going to learn. That's one of the things. That's one of the applications of converting between bases. And so one of the things we're going to learn is what all those ones and zeros mean. Now, why do computers communicate in ones and zeros? Because it's simple, exactly. Ones and zeros can be modeled by simply on and off. So a computer runs on electricity. So the easiest thing for a computer to measure is on and off, signal or no signal. So this is essentially the way that a computer thinks. All right. And we're going to see how those ones and zeros actually become information. And we're going to do that by learning how to convert between bases. Okay. And again, that's just one application. So now a little bit of the mathematical background of what converting between bases is. All right. So what we're used to is we're used to numbers. For example, if I write down 527, everybody knows what that means. 527. Numbers were not always written that way. So I presume everyone is at least slightly familiar with Roman numerals. Okay. So, for example, where we write what we call the digit 3, what did the Romans write? They wrote ///. Okay. But or line. If we write line, does it mean 3? What does it mean? It means 111. That's just the font. Yeah. You can write it in any font you like. Okay. So, right. So, what's the difference between line meaning 3 and line meaning 111? Yes, the difference is the place value. We have place value in our number system. Did the Romans have place value? No. Anytime you see a line or an I, it means 1. Doesn't matter where it is. Not so with our number system. So that's the first thing that we need to understand. That's the main thing, in fact, that we need to understand. All right. So a quick overview in the history of numbers, skipping over some steps. All right, so understanding place value. So back in the day when sheep farming was kind of the big occupation, everyone had to keep track of, or it was important, and eventually they developed a way to keep track of how many sheep they had. So let's say they had a bunch of sheep. What's the first thing that they would write down? They would say, I have this many sheep. Alright. So every sheep gets one mark. These are called tally marks. Well, obviously they couldn't say 1, 2, 3, 4, 5. They didn't have that system. That's a great point. So exactly. So that's the thing. If all you have is tally marks, heaven forbid you have the number that we would now call 93. Heaven forbid you have 93 sheep. Right? If you have all those tally marks, you might as well just have all those sheep there. It's hard to keep track of. So exactly what Hugo said. You need a better way to visually represent this data. And so I'm pretty sure most people have probably seen at some point this idea of grouping. And I think most people have seen where you group by 5s. Is that fair? Okay. So now suddenly that we've done grouping, what is the number that we would associate with this amount? This total number of sheep. 13. Okay. So already it's much easier to conceive of the total amount. Okay. But now we've got an even better way, of course, as like I just said, of writing this down. So I'm skipping over a couple centuries here. And now we get to our number system. So 13. Now, where did that 13 come from? How does that match what the marks we just made? Exactly. So first of all, this represents ones and this represents tens. So the important thing to understand is that that 1 marked there does not really mean 1, as in a single. What it means is a 10. And a 10 is, well, it sounds silly to say it out loud, but it means 10 ones. All right. Where 10 ones is that. So that 1 in the 13 means that. So this is the thing that you learned many years ago in elementary school, and you've kind of forgotten because it's so second nature. But we have to go back and remember this in order to understand what's coming up. Because we're used to thinking of tens, and then what's the next place value? Hundreds, and how do you get 100? 100 is, if you remember playing with those blocks, 100 is 10 tens. So then 10 tens gives you 100. And what's the next place value? 1,000. How do you get 1,000? It's 10 hundreds. Okay. So the idea is that we're grouping things in groups of what we call 10. This is not the only grouping choice. In fact, another grouping choice is what's written down right in front of us. This method of grouping with the tally marks, what do we have groups of there? We have groups of 5. So we can actually make a number system out of that. So how many of the different groups do we have? 3 what?
2 groups of 5 and 1 group of 2.
Exactly. So we have 2 groups of 5 and 3 ones. How would you write that down as a number?
5 plus 5 is 2.
You're thinking in base 10. Think about the number 13. What does the number 13 represent? 1 10 and 3 ones. So now go the other way. but with a different grouping. In this case, we have 2 5s and 3 1s. How would you write that down as a number? 23. You dig?
No, this is not 2 tens. It's 2 5s.
Right. So the difference is that we have to say that we're grouping using 5s. And that's what's called base 5. So in this case, we have 2 5s and 3 1s. So grouping by 5s, or in other words, in base 5, that set of tally marks would be the number 23.
Oh, I understand how you got the 3 before. Oh, because there's 2 5s?
Because there's 2 5s.
So if there are 3 5s other than a 3?
Yes. Okay. So the thing is, so it's going to take, I understand, a little bit to wrap your brain around this, because when you say the number 23, you're like, I know what 23 is. But the entire point is that we have to break down our assumptions that 23 means 2 tens. So what we need to understand is so we're now talking about converting between different bases and what it means to write a number in a different base. So first of all, the notation. So we write it down like this. Now also notice that when you talk about base 5, we use the word 5, F-I-V-E, because you don't want to write down the number 5, because we're no longer sure what the number 5 means in our new world of talking about different bases. So if we write down the word 5, we'll just assume that it's the 5 that the 5 that we're always used to, that we know what it means. Okay. So notice that based on the discussion we just had, we can say that writing down, so the number 13 in base 10 is the same as the number 23 in base 5. And this is the notation. You do it like you write down the word like a little subscript. Okay. And so I'm going to write it down as an equation, because, so what does this mean? So one way to think of this is that in base 10, the number 13 means 1 10 and 3 1s. And in base 5, the number 23 means 2 5s and 3 1s. And are those the same thing? Yes. So here is how you could just write that out in notation, and to show that they're the same. And again, this equation, of course, is written in base 10, regular. Okay. And I also want to show you the picture. So in one sense, the tally marks represents one picture to show grouping. Here's another way to show it. Let's see. We sure will. Okay. Actually, I think I'm going to put this underneath so you can see that what you've got is exactly the same thing. Okay. Right. So you can see that you've got the same amount here. So the difference is the grouping. So in base 10, what do? First we look for tens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 3 1s. The other one, we're going to break it up in base 5, so using groups of 5. So we have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 1, 1. Does that make sense? Okay. So, just a quick note going forward. If no base is written, you can just assume it's base 10, the good old numbers that we're used to. Okay. So you don't suddenly have to go around writing a little the word 10 next to every single number that you write down. Just the other bases to remind ourselves that there's something different going on. Okay. So let's further understand what's happening in different bases. We're going to come back and do some more examples. But the basics of the bases are counting. Right? Who was someone over here before said, what did the sheep farmers do? Did they count 1, 2, 3, 4, 5? Well, with tally marks you can't count, but with different bases you certainly can count. So let's see what counting looks like in different bases. Well, in base 10, I hope and I'm pretty sure we all know how to count in base 10. So how does counting in base 10 go? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, 12, 13, 14, blah, blah, blah. And I'm just going to go to the next interesting number. Let's see. Then we have 98, and then 99, and then what comes next? 100. 100, and then 101, and then we keep going. Okay. So that's counting in base 10. What does counting in base 5 look like? Well, how does it start? 1, 2, no. 1, 2, 3, 4. What comes next? Yeah. Well, let's think about it. Do we... Where is it? Okay. Sorry? Okay. Okay. Well, let's think about this just in terms of the blocks that we had before. So 1 block is 1, 2 blocks is 2, 3 blocks is 3, 4 blocks is 4. What happens when we have that many blocks? We have a group. And how do you write this in base 5? 1, 5, 0, 1s. So this is the number 10 in base 5. One, 2, 3, 4, 10, and then what comes after a 10? Oh, exactly. Then, oh, I know what the problem is. Okay. Then 11, 12, 13, 14, 20. Exactly. Because after 4, what do you have? Another group of 5. So now we've got 2 groups of 5. How do we write that in base 5? 20. Oh, I know. Okay. You know what? All right. 21, 22, blah, blah, blah. Now, what's the next interesting thing that happens? Well, 43, 44, what number comes after 44? 50, really? Right. Does base 5 have the number 50? Because in this case we've got 5 groups of 5. But what happens in base 10 when we have 10 groups of 10? What is that? That's 100. Same thing in base 5. Once you reach the max, once you hit 5 groups of something, once you hit 5 of something, it's the next thing. So the next number is 100.
But you would be 50 at some point, though, right?
In base 5, you never write the number 50. Remember, so the thing is we have to figure out what, when we write one, all these numbers have been written in base 5. So the thing you have to figure out is, what does that number actually mean? Right? Because, for example, we know, let me just put it in here because that's a number that we know. In base 5, when you count to 23, is that the same 23 that we're used to? No. In base 10, what number is that? No.
Oh wait, base what?
When you write 23 in base 5, what does that mean in base 10? It means 13. So when I write 100 in base 5, what does that mean in base 10? No, we don't know yet. We have to figure it out.
It means 45.
No. Because 40 doesn't mean 40, remember? 30 didn't mean 30, 20 doesn't mean 20, and 10 doesn't mean 10. So one of the next things we're going to learn is, what do those numbers mean? But the thing I want you to realize is, if you're thinking of this as an odometer where the numbers are ticking off, when do we go to the next column in base 5? As soon as you hit a 5. Okay. So, let's think about, so let's think about this. What is the largest digit in base 10? 9. Right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. But now, what is the largest digit in base 5? 4. Right? As you never see 5, think of it as the odometer clicks over to the next place value. So, give you one guess, what's the largest digit in base 8? 7. Exactly. So in base 8, what happens when you count past 7? Right. 10, or wherever you're at, you go to the next place value column. Right? So, for example, in base 8, what number comes after 17? 20. Because it ticks over to the next place value column. So base 8, if you're counting, looks like 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20, 21, etc. Okay. What about base 3? What's the first number? 1. Next number? Next number? Yeah. And then? Yeah. 21, 22. I'm sorry? Yeah. Base 3, there's no 30. So we're already at 100. Are
you making these things up?
Absolutely not. Okay. So the thing we have to do now is, so now again, just like tally marks, if we want to figure out what an amount is, we can always just count from the beginning. But we don't want to do that. That's the whole point of having a number system. So the thing we're going to do now is figure out, when you write a number in a base, what does it mean in base 10, which is the base that we're used to. So in order to do that, you have to figure out what is the place value of each number. In base 3, when you write 100, what does that 1 stand for? In base 8, when you write 21, what does the 2 represent? What does the 1 represent? Etc., etc. Okay. So, first let's talk about place value in base 10. So, in base 10, we'll go from smallest to largest. What's the value of the smallest place value? Okay. These are 1s. What about the next place value? These are 10s. Now what about the next place value? 100. Now how did you get 100? 10 times 10. Also written as 10 squared. And what's the next place value? 1,000, which we can also write as 10 to the third. And the next place value? 10 to the fourth, etc., etc. So this is really our system of keeping track of how much each place value is worth. When you're in base 10, the column, each place value is worth 1, 10, 10 squared, 10 to the third, 10 to the fourth, 10 to the fifth, etc. So, how do you think it works in base 5? What is the smallest place value? 1. It's always 1s, right? And what's the next one? Next one represents how many 5s you have. What about the next column? The next column represents 5 squared. And what is 5 squared? It's 25. And what about the next place value column? 5 cubed. And we should figure out what that is. It's 125. What about the next place value? 5 to the fourth. So we're going to want to figure out what that is. It's 625. And what about the next one? 5 to the fifth. And we're going to want to figure out what that is. It's 3125. I think you get the idea. Yeah.
In base 3, so it goes from 22, it doesn't go to 41, 42.
In base 3, exactly. Because do we have a 4 or do we have 40 in base 3? No. What's the biggest digit that we use in base 3? 2. Because what happens when you get to 3? What happens when you try to get to the digit 3? It becomes a 10 or it goes to the next place value. That's the whole idea. Okay. So now let's go ahead and figure out base 3. What are our place values? So the lowest column, always a 1. What's the next place value? 3. Groups of 3. What is the next place value? Next place value is 3 squared, which is 9. What's the next place value? 3 to the third, which is 27. And the next place value? 3 to the fourth. And we should figure out what that is. It's 81. So let's actually take this information and figure out, for example, in base 3, what does the number 100 mean? So the way to figure out what the number 100 means is think about what all the place values mean. So the first place value is a 1, next is 3, and next is 9. So the number 100 is really what number? No.
Oh, 900.
No. The number 100 tells you that you have 1 of something, then 0 of something, then 0 of something. So what do you have? No. Remember that that's not a number. Those are place values. No. Okay. Sorry, let's go back. Okay. So let's do this on numbers that we already know. Okay. Exactly.
Because we don't see like in the base 5, we don't see a 10,000, we just see how many.
Right, exactly. So that's why I'm going to do this. Hold on, I got to make some room here. Okay. Cool. All right. Okay. Okay. So remember what we said before. 13 in base 10 is the same as 23 in base 5. So what does that look like in terms of place value? Well, first let's write things down in base 10. So in base 10 our place values are 1, 10, 100, etc. So how do we fill this number in? It's 13. And what is that? And what does the number 13 mean? It means you've got 1, 10, and 3 ones. Now let's look at the base 5 number. The base 5 number, you've got 1, 5, 25, blah, blah, blah. So what number do we have here? 23. So what does that number mean? 2 5s and 3 1s. You dig? Okay. So that's how we use this little, if you like, this place value notation to figure out what a number is actually telling us. So now, let's go back and look at the number, what did I say? 100 in base 3. Let's actually figure out what number that is in base 10. So we're in base 3, so what are our place values? What's the smallest one? 1, and then 3, and then 9. Okay? So, now we fill in the number 100. So what does the number 100 actually represent? 1, 9, and then 0 of everything else. So what number is this? It's the number 9. You dig? Okay. So another way to confirm this is just the simple, we're never going to do this again, but let's just go back and look at the base 3 counting. Well, we've actually written out every single number, so 1 must be 1, 2 is the same as 2, 10 is the same as 3, 11 is really 4, 12 is really 5, 20 is really 6, 21 is really 7, 22 is really 8, and 100 is the 9th number. So it's 9. So that's another way to see it.
So like these numbers, it is not like, it doesn't go to like 50 or 30 or like 20, then it'll go 1. Like if it, let's say it was 2, it would have been 100.
Oh, if it was base 2?
Yeah.
Base 2 is tricky because it changes so quickly. So we're going to come back to it, but I'll just to answer your question. After 1, we'd like to write the number 2, but we can't So what do we write? What comes after 1? 10. Next place value.
Then 4 would be 20.
But we don't have
Oh,
we
you
don't have the
yeah,
number
that's
2.
what I mean. Like, you know,
Right.
instead of like just put a 20, it would be 100. It's like a 110, then 2.
What comes after the number 10? 11,
Then 100.
and then 100. Right.
So there's no like 20, 40. Or
In base 2, no.
one,
It's just ones and zeros. Exactly. So you should maybe you're starting to connect the dots, and we're going to come back to that example later. Okay. All right. Okay. So now a little exercise to help us bring together both the thinking and the calculations. In base 5, what is the integer right before 100? Right. 44. So that's backwards of the thing that we thought of before. I said, what comes after 44? And you said, oh, it can't be 45, so it's got to be 50. Oh, it can't be 50, so it's got to be 100. So just going in reverse, the integer right before 100 in base 5 is 44. Okay. Another way to think about this is that in base 5, what's the biggest digit that you're allowed to have? Is 4, exactly. So in order to get to 100, the number before that has to have 4 in every column. In the same way that if I say what's the number before 1,000, in base 10, what's the number before 1,000? You know it's 999 because everything has to be a 9 before the odometer flips, so to speak. Does that make sense? Okay. So the only thing is that in base 5, the biggest digit isn't 9, the biggest digit is 4. Okay. But now let's actually check out what this means. This is 100 in base 5, and this is 44 in base 5. Let's figure out what two numbers we're actually talking about. And by actually, I mean in base 10. So let's check that out. Okay. So first of all, let's take the number. Well, 100 is the easiest one. What is 100 really mean? What is the number 100 in base 5? What number would that be in base 10? What is it really worth? So in order to figure that out, you have to remember that these numbers are written in base 5. So what are the values of the columns? 1, 5, 25. So when you say 100, what is that really? What number is that really? This is really 25. Now let's do that with 44. So what number is that? And how can we figure out what number this is? Exactly. This tells you that there's 4 5s and 4 1s. So how can we write that out so we can calculate that? We'll just write that as an equation. This tells you that you've got 4 5s, which is 4 times 5, and then you've also got 4 1s, which is 4 times 1, and of course we add them together. So what does that give? 24. So when we write 44 in base 5, that is 24 in base 10, or in other words, the number that we're used to. And we write 100 in base 5. What that really means in base 10 is 25. Does that make at least a little bit of sense, if not complete sense? Alright. I don't expect this to make complete sense yet. So we're now going to get into the examples part, where how do we actually convert between bases? And I think based on this last example, you've started to see how to actually do that. So, okay. So for example, suppose I have the number 2021 in base 3. Let's convert that to base 10. How do you do that? Well, you make your little place value picture. So what does each place value represent? Starting from the smallest, that's always the easiest. Okay. So starting from the smallest, what's the smallest in base 3? What's the smallest place value? 1, and then 3, and then what's next? 9. Right, 3 squared, which is just 9. We're going to write it like that from now on. And then next, 27. Right. And how many place values do we need? How many digits is the number? It's only 4 digits, so that's all we need. Okay. So now let's fill it in. This is the number 2021. So what is this equal to? We've got 227, so that's 2 times 27 plus. Right. So if you like, plus a 0 plus 2 times 3, and then plus 1 times 1. So work all that out. It's 54 plus 6 plus 1. This is 61. Yes. So if you wanted to be precise, or if you wanted to be excessively clear, you could write down a 10. But remember what I said, if we don't write down what the base is, you can just assume that it's base 10. So, and it's precisely for this reason, because you wouldn't want to have to write in the calculation 10, 10, 10, 10. You wouldn't want to have to do that every single time. So that's why if we don't write it, we just assume that it's regular base 10. Make sense? Okay. So mostly just for simplicity and not to get things all sloppy. Okay. So let's do let's do this one more. Let's do another example together. So we've got 4,236 in base 7. And let's convert that to base 10. So how do you do that? What's the first thing you need to do? First thing you need to do is write down your place values. So 1, 7, 49. Now would you think a little bit? Nope. 343. Yeah, how do you get to the next place value? How do you get when you're at 7, how do you get to the next place value? Times 7. So when you're at 49, how do you get to the next place value? You don't square it. You multiply by 7. Because think back to base 10. When you're at 1,000,000, how do you get to the next place value? Multiply by 10. Next one is 10 million. Exactly. So it's so simple that it's hard, because it's changed one underlying assumption. The underlying assumption that we always use is that we're working with tens, and we're no longer doing that. So you really have to remember the basic. You have to go back and remember what you learned in elementary school. But we have to do it not with tens, which is hard. Okay. So now we can stick this number in here. 4236. And we can say what this equals. So what does this equal? How do we set this up? And that equals 1372? Okay, I'll take your word for it. Oh, the first one's 1372, not the whole thing. Okay. 1372 plus 98 plus 21 plus 6. Sorry? Oh, 1497. Okay. 1497. We've got 4 times 343 plus 2 times 49 plus 3 times 7. Well, what's 3 times 7? Okay. Alright. So, is that starting to become more clear? Alright. Yeah. So, the first thing I expect you to get is how to do it. Very last will come comfort and understanding.
Do we have to convert it to like a base 5 something?
Yes.
7 to a base 5?
That's coming up. Okay. So, next example. Convert 8,347 in base 4 and convert that to base 10. Okay, so let's talk about it. Okay, so you get 1. Uh-huh. 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 No, just tell me the whole thing altogether. 583. Okay. Is that what everyone got?
Mm-hmm.
Okay. So that's fantastic, and it's wrong. Yeah. Right. What's the problem? What base are we in? We're in base 4. What's the problem?
4 is 10.
If we're in base 4,
And 4 it would be 10. Because it's 3 10.
in base 4, this number does not exist. No, no answer. Number doesn't exist. What digits do we have in base 4? 0, 1, 2, 3, and that's it. This number doesn't exist. So what you got? So look. So you guys should be happy. You guys should be happy because you did the procedure in exactly the right way. So that's good.
But we didn't realize that base 4 only has base 2.
Exactly. But you didn't realize that this number does not exist in base 4.
Then how come your 7 is
It does not.
well, that they can do in a bucket if they
Oh, because it only has up to 6, I thought.
Oh, no, 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 no. What? So when we did the problem for base 7 and across the top we were at 343, 49, 71, those aren't numbers in base 7. They're the place values. And we're writing the place values using base 10 because that's what we're familiar with. You dig?
No, but I don't understand why there's 3 value 7 and 3 in not.
Oh, okay. Well, what comes after 6? Okay. Right. So right. So when we say what comes after 6, you have to ask me what base are we talking about. So the thing that okay. So here's the thing. If I said what is 3 times 4, you better hope that I'm asking you that in base 10. Right? If I say what's 3 times 4 in base 6, you're like, I don't know. Right? We really only know how to do calculations and this other fancier stuff in base 10. So right now, all I'm asking you to do is convert numbers between some other base and base 10. I'm not asking you to do the fancy stuff. So when I say we've got the number 4,236, but it's in base 7, what is it converted to base 10? The only way we really know how to count and do arithmetic and do all those things is in base 10. So when I say the place value is 7, if I was going to write the place values in base 7, it would be ones, tens, hundreds, thousands. But the whole point is to represent it in base 10, which is what we are familiar with. So in base 10, the first place value is 7. Excuse me, first place value is 1. Next place value is 7. Next place value is 49. Not yet?
No.
Okay.
Because you're asking us exactly the same thing as base 4. So why?
No. But so here's the difference. But here's the difference. Here I've written down the number 8347. So I've used 8, 3, 4, and 7 as digits in a number. Am I allowed to do that in base 4? No. Those digits, some of those digits don't exist in base 4. Like 8, 4, and 7. Exactly.
So you can prove the place value for the digits that are the ones that are wrong.
Exactly.
I don't see that.
Yeah. In base 4, those are always the place values. 1, 4, 16, 64, 256, 10, 24. We go on. Those are all the place values. Okay. All right. Okay, so I'm going to give you a real one now. And in addition, I'm going to give you one as Terrell was asking about. I'm going to give you one that's from base 2. So, actually, let me do it like this. Okay. So work this one out. So let's talk about how to do this problem. So who can help me out? Someone else? Okay. Hugo, you were pointing to yourself, so go ahead. Okay. Uh-huh. Jacob?
That's not correct. It's 1, 2, 4, 8.
Oh, I thought I was
Guess we better fix that. Okay. Okay, so let's do it again. So we get 16 plus 1 times 2 plus 1 times 1, 19. Okay. So good? All right. Okay, so last thing I want to talk about today is bases bigger than 10. So, for example, how can you have something like base 16? To figure out how to write these things. So, the first thing we have to confront is how can you have all these digits, right? Because we saw in base 6, for example, what's the biggest digit?
5.
The biggest digit is 5. So if you had something, for example, base 16, what would the biggest digit be? The biggest digit is 15. That doesn't seem to make any sense because we're thinking 15 has 2 digits, so how can that doesn't make any sense? So what we need to do is we need to invent some digits. Because if we're actually going to be in base 16, what do we need a digit for? We need a digit for 15. What else do we need a digit for? 14, 13, 12, 11, 10. If we're really going to be in base 16, if we're really going to commit to this, we actually need a single digit for all these things. So we're going to have the only digits that we're used to working with are 0 through 9. We have to make up 6 more digits. Okay. So let's do it. It turns out that base 16 is actually used very commonly with computers. We'll get to more computer applications in a minute. And the name for this system is called the hexadecimal system. Hex is 6, decimal is 10, so there's 16, base 16. And the way that they solve this problem is after you have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, should have a 0 in there. Then we just go A, B, C, D, E, F. So in base 16, we have the digit A. The digit A is equal to what in base 10? It's 10. Exactly. Because once you get to F, what is the next number? Right, 16, but in base 16, how do you write that? 10. No, this is 10 written in base 16. Yeah, remember all these numbers written here are written in base 16. So, right. So this is written in base 16, but let's count it out in base 10. 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4 is 4, 5 is 5, 6 is 6, 7 is 7, 8 is 8, 9 is 9. A is 10. B is 11. C is 12. D is 13. E is 14. And F is 15. Now we're in base 16, so what's the biggest digit? 15, which is F. So what's the next number after F? 10. No, it's 10. Just like in base 3, what comes after the number 2? 10, because you've maxed out your digits and you go to the next place value. So once we hit F, they're not placed, those are actual digits. So now the thing is, we could have gone all Prince on it and come up with like weird symbols. But well, I guess a little bit about computer coding history might be interesting here. This is actually used in computers. So when they were looking, so when they said, well, we ran out of digits, we'd like to have 16 digits, what are we going to use? Well, in computers, the first thing they learned how to encode were numbers. What do you think is the next thing that they learned how to encode with computers? Letters. Exactly. So the next easiest thing for them to use was letters. So they just use letters. So the thing is, you have to know that when you're talking about base 16, A doesn't mean A. It means 10. And F is the biggest digit. So once you reach F, the next number is 10. What's after 10? 11, 12, 13, 14, 15, 16, 17, 18, 19. And what's the next number after 19? What's the next number after 19? No, it doesn't go to it doesn't have to go to 20. Because what's the next digit after 9? No. A. So what's the next number after 19? It's 1A. It doesn't need to reset because we're in base 16. So we can keep counting. 19, 1A, 1B, 1C, 1D, 1E. And what comes after 1E? 1F. And what comes after 1F? 20 or 20. You're allowed to go all the way from 0 up through F before you have to reset.
So you would have a 160, you would have a 1600 then.
You wouldn't, I'm sorry?
You wouldn't have a 160. You would have like a 1600.
Well, see, this is the trick, because what's tricky about bases bigger than base 10 is that we have all the digits that we're used to, plus we have other ones. So there's no such thing as saying you would never write 97, because you can, of course you can write 97. You really sort of have to think about it in reverse. In base 16, you can write the number 1A. And what we would now say is, well, in base 10, we would never write the number 1A. That's what we have to say. Right? Before we were talking about taking away digits, digits not being available. Now we've got extra digits. Okay. So what are the place values in base 16? 1 and then 16 and then 16 squared, 16 cubed, etc., etc. And then we can work it out with the calculator what those things equal. So it turns out, there you go. 16 squared is 256, 16 cubed is 4096, 16 to the 4th is 65,536. So I said before, this comes up in computer programming. That's the main reason why I've chosen base 16. We'll get into a lot more next time where this. We've already talked a little bit about computers being computer data being written as ones and zeros, and we already saw what base is that. That's base 2. So we've already talked a slight amount about why base 2 appears in computer programming. We're going to talk a lot more about it next time. And we're actually going to do some fun computer-like operations using base 2. A quick comment. Some computer applications, for some reason, at some point, someone said, let's write this stuff down in hexadecimal base 16. I don't know why, but they did. So, for example, and I'll give you one example of where this is used from. If you ever, I don't know if anyone here has any coding experience, certain things are written down in as hexadecimal codes. So, for example, when you write down colors, you may or may not know that colors in light, colors break down into the 3 primary colors: red, RGB, red, green, and blue. Actually, that should be 0000FF. Or is it RB? RGB, yeah. So I have to change this. This is green. I think this is right. Okay. So what you have to tell the computer is how much red do you want, how much green do you want, and how much blue do you want. And once you tell the computer that, it determines the intensity of each of those primary colors, and then it combines them, and you get whatever color is projected. So the way that this is encoded is using hexadecimal. So what this really is this. So we've got 3 two-digit numbers here. The first two-digit number is how much red. The second two-digit number is how much green. The third two-digit number is how much blue. So in this case, how much red is there? There's 0. 0, 0, that's very easy, that's 0. How much, the third one, how much blue is there? There's also 0. How much green is there? Right. It's FF. So as far as two-digit numbers go, is FF, is that big or small or in the middle? How big is the digit F in hexadecimal? It's the biggest number that you can possibly have. So what this is saying is we want as much green as possible and no red and no blue. So this code represents green, all green. So there you go.
So for a lighter shaded green, you would put like a smaller letter.
It would be a lower intensity, exactly. Also, if anyone ever shopped for computers, do you ever notice that they say 256 colors, or maybe 1,000, or maybe 4,096 colors? All those different. Has anyone seen 256 colors? That sort of thing written for a computer spec. Well, that is where 256 comes from. It's 16 squared. Okay, so that was your fun little bit for today, and we will pick up with this in the next lecture.